Hey everyone, in this video we are going to discuss today's LeetCode contest, that is weekly contest 516. So let's start with the first problem. In our first problem, we are given that you are given a string S consisting of lowercase English letters. Construct a binary string by replacing each character in S with the 8-bit binary representation of ASCII value, including leading zeros, while preserving the original order of the characters. You need to return true if the resulting binary string is a palindrome, otherwise you need to return false. A binary string is a string which contains only characters 0 and 1. A palindrome is a string that reads the same forward and backward. Okay, so the problem statement is simple. You are given a string S and you need to convert the string S into a binary string, right? By converting each of the character into its ASCII value. By converting each character's ASCII value into 8-bit binary, right? And appending it to the string. So for example, if you see the example of first sample test case, here f and f, the ASCII value of f is 102. So if you will convert it into 8-bit binary representation, this is the one, right? 8-bit binary representation of 102. So f and f, you will append these two binary representations. So this is the binary string you will get from the original string f and f, right? So you need to check whether this is a palindrome or not. Here in this case you see that this is the palindrome, this binary string is a palindrome, so your answer is true for this sample test case. If you see an example of second sample test case, if you will convert each of the character here, each of the characters ASCII value into the binary string, you will see that these are the binary representations of the ASCII values of each of these characters L, E, E and T. If you will append all these binary representations, this is your final string. You need to check whether your final string is a palindrome or not. Here you can see that this is not a palindrome, so your answer is false for this sample test case. So how you will solve this problem for a general given string S? You will do the same, right? You will convert each character's ASCII value into binary representation, append it, and finally check whether the final string S is palindrome or not. So let's see the code also. Here what we did is we took a string variable b, which will store the binary representation of all the characters. So here we are iterating over each character of string S, find its ASCII value. It's simply ASCII of value of u is, you convert it into the integer. In C++, here is how you can directly get its ASCII value. Now iterate over all of the bits starting from 0 to 7, and for each bit check whether this ith bit is set or not. If ith bit is set in ASCII, that means your current bit is 1, otherwise your current bit is 0. At the end, just check whether this is palindrome or not. Take two variables, take two pointers I and j. I is starting from 0 and j is starting from end of the string b, and check whether if there is any pointer where b of I is not equals to b of j. In that case, you know that this is not a palindrome, just return false. Otherwise, at the end, just return true, as it is a palindrome. So this is how we can solve this problem. Let's move to the second problem of today's contest, that is find all numbers disappeared in an array 2. Okay, so in this you are given an integer array nums and two integers lower and upper. A missing integer in an integer is an integer in the inclusive range lower to upper. that does not appear in nums. Return a 2D integer array where each element is of the form start to end, representing a contiguous range of missing integers. Return the ranges in increasing order. If there are no missing integers, return an empty array. Note, a consecutive missing integers should be grouped into a single range. Okay, so the problem statement is simple. You are given an array nums, okay, and you are also given a range that is starting from lower up to upper. Okay, now what do you need to solve in this problem? You need to return a group of ranges such that each range contains the missing numbers in this given array nums, right? So how you can solve this problem? So let's take an example of this first sample test case. If we take an example of this sample test case, so we are given this range lower to upper, right? That is 1 to 12. We need to find all of the range in this given range that in all of the ranges in this range where all of the integers are missing in the given array nums. Okay, so before coming to the ranges, missing ranges, first let's find all of the missing integers in this range 1 to 12. So what are the missing integers? 1 is missing, right? Because 1 is not there in nums. 2 is missing because 2 is not there in nums. 3 is not missing because 3 is there in the nums array. Then 4 is missing, 5, 6, 7, 8, 9 is there. So, and 7 is also there, right? So this is also not missing. 9, 10, 11, 12. These are the only integers which are missing in nums array in this range 1 to 12. So let's group these integers into consecutive ranges, right? So first we see that 1 and 2 is a consecutive group of integers. So let's group them into one range. 4, 5, 6. 4 to 6 is the next range, right? We cannot take 4 to 8, right? Because 7 is not a 7 is missing here, so this is not a consecutive interval, right? So starting from 8, you will have to take 8, 8 because 9 is not there, right? So this is the one consecutive range. Then 10, 11, 12. This is a consecutive range. So this is your answer for this sample test case. We have four ranges in increasing order where each range represents all of the missing integers in this nums array. Okay, so this is our answer for this sample test case. Now let's see how you can solve this problem for a general given array nums and this lower and upper range, and you need to find all of the missing integer ranges. So you will do the same thing, right? You will create a Boolean array, right? Let's say missing Boolean array missing where missing of I represents whether I is present or not. I is present or not, right? So if missing of I is true, it means that I is not present in the original array nums, right? And if missing of I is false, it means that I is present. Okay, so once you created this array, this is very simple. You created this array, a boolean array, and iterate over the nums array, and wherever, for all of the integers present in nums array, you will just mark missing of I equals to false. Okay, so once you have this missing array, now what you will do is you will start from lower, and move up to upper. Okay, iterate up to upper, and you will see, you will try to find the maximum range, right, which is maximum range of integers which are missing in the nums array, right? So as you know, the missing array will look like this: 0 1 1 0 1 0 1 1 1 1 0 1 1 1 0 0 0 1 1, right? So your missing array will look like this. So what you will do is, this is your lower, means starting point, and starting point of the range, and this is your upper index, that is end point of this range, right? So you will just iterate, and wherever you see the consecutive ones, you will just append it to your answer, right? So here in this case, lower plus 1 comma lower plus 2, this is one range, this is one range, this is one range of missing integers, this is one range of missing integers, this is one range of missing integers. So this is very easy to calculate, and just append all of these ranges into your answer and just return your answer. So let's see the code also. We have done the similar thing. We created a boolean array missing, right, of size upper plus 1, and we marked all of the integers that are present in nums array false in the missing array, and then we took a vector of int answer, and we are starting from lower. Okay, so wherever we see that missing of I is true and missing of L is false, what does it mean? It means that ith integer is missing in this nums array, and the starting point of range, that is L is not missing, right? Then just assign L equals to I, right? Because we want to start our range from an integer which is missing, right? For example, this one, we are always going to start from an integer which is missing, right? So just assign L equals to I and continue. Otherwise, if this is not the case, then what we will check? We will check that if missing of L is true, means L, starting point of our array, starting from our starting point of our range is missing, and missing of I is false. What does it mean? It means that ith integer is not missing. Then we will just push this range to our answer, L comma I minus 1. Why we didn't pick I? Because I is not missing here. And just assign L equals to I. At the end, if upper means the end of this range is missing, then just insert this L2 upper into our answer, and at the end just return the answer. So this is how we can solve this problem. Let's move to the next problem of today's contest. So in this problem, you are given an integer array nums consisting of positive integers and an integer k. The prime factor set of a subarray is a union of distinct prime factors of all its elements. Return the length of the longest subarray whose prime factor set contains at most k distinct prime factors. If no such subarray exists, return 0. A subarray is a contiguous non-empty sequence of elements within an array. A prime number is a natural number greater than 1 with only factors 1 and itself. So I hope you got the problem statement. It's pretty simple. You are given an array, integer array terms, okay, and you are also given a positive integer k. Now you need to check. You need to find the longest subarray, longest length of a subarray, such that the subarray contains no more than k distinct prime factors, right? So how we will solve this problem? So let's take an example of this first sample test case. If we take the example of first sample test case, here is our nums array we are given, and this is the value of k, which represents the maximum number of prime factors we can have in the subarray, right? So first of all, let's try to find all the prime factors of each integers in this nums array. Starting from 7 has only 7 as the prime factor. 6, it has 3, 2, 3 as the prime factors. 10, it has 2, 5 as the prime factors. For 12, they are 2, 3. Is there anything else? No. 2 and 3 are the only prime factors. Now let's take 11. 11 has only one prime factor, that is 11. So these are the prime factors. Now you need to find the maximum length of a subarray which contains at most k prime factors, right? So starting from index 0, how many integers can you take? You can take only first two integers, that is 7 and 6, because if you take first three integers, you will see that the number of prime factors are 2, 3, 5 and 7, right? And they are 4. So this is not allowed. Only maximum 3 are allowed. So if we start from 0, we can only take integers up to index 1. So 0 to 1 is a valid range, right? Valid subarray. Now starting from 1, how many integers can you take? What is the maximum length of subarray can you take starting from 1, index 1? You will say that you can take up to this index, that is third index, 1 to 3, right? Because if you take 1 to 4, then notice that the number of distinct prime factors are 2, 3, 5 and 11, and they are 4, and it is not allowed, right? Because maximum 3 is allowed. So starting from 1, you can only take up to index 3. So 1 to 3 is also a valid subarray. Starting from 2, you can see that you can take, can you take 2 to 4? You will say that no, we can't take. Why? Because the total prime factors here are 2, 3, 5 and 11. They are 4, and 4 is not allowed. So you will be only able to take 2 to 3. So 2 to 3 is a valid range. Similarly, now let's move to index 3. Can you take 2 and 4? Yes, you can take, because there are only 3 prime factors here. And 4, this was 3 actually. Starting from 3 and 4. Okay, for the last index, starting from 4, you can only take 4. So these are the only valid subarrays, right, starting from each of the index. So what is the maximum length of the subarray you can get? Maximum length of the subarray is any of maximum length of the subarray is, this is the one, right? What is the maximum length of this? 3. So for this sample test case, your answer will be 3, right? That is this subarray starting from first index to 3. Okay, so how you will solve this problem for a general given array? So we can see that the constraints are quite high. We cannot analyze each of the subarray, right? If you go with the brute force approach, what you can do is you can iterate over each subarray, right, in order of n square, and in each subarray what you can do is in each subarray just find the set of all prime factors, right? For each prime factor, get all of the for each integer in this array, let's say iterate over, what I'm saying is I'm just explaining the brute force approach, iterate over each of the subarray, right, L to R, and for each integer in this subarray nums of I, find all of the prime factors, right, and then store in a set, right, set S, right? Do this thing for each of the integers, and these prime factors you can find with the help of sieve algorithm, right? So this sieve algorithm will give you prime factors in order of log n time, right? Log of a time a max, where a max is the maximum integer in nums array. So you can find each of the integers prime factors and store in the set, and at the end check whether the size of this set, if the size of this set is less than or equals to k, then this is your answer. Maximize your answer equals to maximum of answer comma length of this subarray. What is this? R minus L plus 1. So this is how you can solve this problem, and the time complexity of this solution is order of n square for iterating over each of the subarray, and for calculating prime factors for each integer it will take log of a max, log of a max. Okay, but you see that this solution will not pass here because n is order of 10 to the power 5. So we will have to improve this solution. How we can improve this solution? So we will follow a 2 pointers approach. Okay, let's take 2 pointers I and j, initially starting from, let's take 2 integers, 2 pointers I and j starting from I equals to 0 and j equals to 0. Okay, at any point, let's say I represents your rightmost interval and j represents your rightmost point of your interval, current interval, and j represents the leftmost pointer of your current interval. Okay, now what we will do is each time we will increase I by 1, and also we will maintain a set, right? We will maintain a set. This set will contain all of the prime factors of each of the integers present in this range j to I. Okay, we have this set. Now what we will do is each time we will increase our right pointer by 1. Okay, I to I plus 1. Now you know that when we increased I to I plus 1, we will have one new integer in our current segment, that is nums of I plus 1. Nums of I plus 1. right? We got a new integer, right? Because we moved our right pointer by one position rightwards. Now what you will do is find all of the prime factors of this nums uh, integer and put all of the prime factors into this set. Okay, now what we will do what you will do is you will, in this loop itself, apply a while loop, right? Apply a while loop. In this while loop, what you will do is in this while loop you will keep on incrementing your value of j okay. So sorry, what I was saying is, so we were following this two pointers approach. Okay, and in this two pointers approach, what we will do is we will take a set S. This set will represent all of the prime factors, all of the prime factors of all of the integers present in this segment j to I. Okay, and now what we will do is each time we will move our right pointer, that is I, by one position rightwards. Okay, now as we moved our right pointer by one position, we got a new integer in our current segment, that is nums of I. Find all of the prime factors of this nums of I and put these prime factors into our set S. Okay, now it may be possible that our current set S has more than k prime factors, right? Because earlier our segment was good, this segment was good, it means that size of this set was less than or equals to k. But as we got our new integer into this segment and we put all of the prime factors of this integer into our set, it may be possible that the size of our current set is greater than k because of the new prime factors we got for this integer, right? So what we will do is we need to move our left pointer, that is j, rightwards until our size of set is less than until our size of set is greater than k. So what we will do is we will just write a while loop until the size of our set is greater than k. Write this while loop. Okay, and here what you will do is you have your current integer of your left pointer is the integer corresponding to your left pointer is nums of j. So what you will do is find all of the prime factors of nums of j and remove these prime factors from your current set. Okay, and once you removed all of the prime factors of nums of j, check whether the size, no, just remove all of the prime factors of nums of j and increment your left pointer, right? In the next iteration your while loop will check whether your size of s is still greater than k. If your size of s is still greater than k, you will again take the next pointer nums of j and find all prime factors, remove from set s and increment your left pointer. So you will keep on doing this until your size of s is greater than k. So this is a two pointers approach. Each time you are incrementing your right pointer by one position and you are maintaining a left pointer j such that your I to j, that is your j to I segment, is a good segment, which means that your all of the prime factors, all of the distinct prime factors of each integers present in this segment are less than or equals to k. Right? The count of all of the distinct prime factors in this current segment from j to I is less than or equals to k. So this is how we can say. Also, we will take an answer variable, right? So each time after running this while loop, we'll just maximize our answer, right? Maximum of answer comma I minus j plus 1. Okay, and then just at the end, after iterating all of the integers, means after incrementing your I up to 0 to n minus 1, at the end your answer will be there in this answer variable and just return your answer. So this is how you can solve this problem in order of n log of a max. Okay, so as we followed this two pointer approach, it will take order of n time, and calculating the prime factors of each of the integers, it will take order of log of a max, right? And for maintaining this set of distinct integers, distinct prime factors, we will take an unordered map, right? So unordered map is usually order of 1, so it doesn't count into the time complexity. This is the final time complexity which you will be having, and it is sufficient to pass the given constraints. So if you are still not able to get the solution, let's try to understand with the help of code. So what we did here is, for pre-computation, we have calculated the sieve, right? We have calculated the smallest prime factor for each of the integer with the help of sieve algorithm. Okay, so this is what we are doing here. This is standard sieve algorithm. It helps us get the smallest prime factor of each of the integer. So what we do here is, starting from 2 up to square root of the maximum integer, we will do so in the inner loop we'll start from I square, okay, and iterate up to j is less than the maximum integer, and each time add I to the j. Here we will check whether the integer corresponding to j has smallest prime factor equals to j. If this is the case, that it means that this smallest prime factor has not been, the smallest prime factor of j has not been updated yet, right? If this is the case, then you know that I is the smallest prime factor of j. Okay, so this is how we can calculate the smallest prime factor for each integer. And in the constructor itself, we have just initialized our smallest prime factor array, and we called sieve algorithm to calculate all of the smallest prime factor corresponding to each integer. Okay, so here let's come to the main part of the problem. Okay, so here we are maintaining this. So for maintaining this set of distinct prime factors, we are taking this unordered map of int comma int. F, what does it represent is, f of I will represent the distinct, f of I will represent the frequency of I. Okay, here let me also write a comment. F of I will represent the frequency of I. Okay, now let's take a count variable. count stores the number of distinct prime factors in the current segment, and answer will represent the maximum length of the subarray. Okay, so let's iterate over I, starting from I equals to 0, j equals to 0. Okay, j to I is our current segment, right? J and I are the pointers which we are taking corresponding to our current segment, and each time we will increment our I pointer by one position rightwards. Okay, so first of all, let's get all of the prime factors of our current integer nums of I, right? Because nums of I we just got into our current segment. So this is how we calculated the prime factors of nums of I using the smallest prime factor array. Okay, now let's iterate over the prime factors p. So we check that if f of u equals to 0 means the frequency of prime factor u is 0 in our unordered map, which means that in our current segment there is no prime factor u, okay, whose value is u. So in this case we will increment our count by 1. Count represents the number of distinct prime factors, represents the number of distinct prime factors. Okay, so if f of u equals to 0, it means that the frequency of u is 0 in our current segment. It means that u does not exist in our current segment. In this case, increment the count by 1 because we just got a new prime factor into our current segment, and also increase the frequency of u. Okay, now our work is done for incrementing I. Now let's check whether count is greater than k, right? If count is greater than k, it means that we will have to move our left pointer, that is j, rightwards until our count is greater than k, because we are only considering good segments where the count is less than or equals to k, means the number of distinct prime factors are always less than or equals to k. So we have written here this while loop, and we will run until our count is greater than k. So let's clear this prime factor array and calculate the prime factors of this current integer, that is nums of j. Once we have calculated the prime factors, we will iterate over these prime factors, and we will check that if f of u equals to 1, it means that this is the only remaining prime factor in our current segment. In this case, after removing this nums array, we know that we are going to have one less prime factor. So just decrease count by 1 and also decrease the frequency of u and increment our left j pointer. At the end, we know that we will be having j to I as a good segment. So just maximize our answer I minus j plus 1, and at the end just return the answer. So this is how we can solve this problem using 2 pointers and sieve of Eratosthenes, I think, sieve algorithm in order of n into log of a max time. Now let's move to the fourth problem of today's contest. In this problem, actually I was not able to completely submit this solution, means my solution was not submitted. In some of the test cases, a few of the test cases, this solution exceeds the time limit, and I also see that there are there are 0 accepted solutions. So I don't know if there is any problem with the solution of the author, or they are expecting a very optimized solution. So this problem solution, so I was able to solve in this n root n time using square root decomposition. So I will explain this solution, right, n root n time, and if there is any better solution we can explore later. So, but for now I will just explain you n root n time solution. So let's first try to understand this problem. So in this problem you are given an integer array nums, an integer k. You are also given a 2D integer array queries, where queries of I represents a range L to R, which represents the subarray from nums of L to nums of R. For each query, the subarray L to R is considered valid if it contains exactly k distinct numbers and the frequency of each number in the subarray is even. Note, the frequency of a number in a given array, in a given subarray, is the number of times it occurs in that subarray. Return the Boolean array answer, where answer of I is true if this subarray is valid and false otherwise. A subarray is a contiguous non-empty sequence of elements within an array. Okay, so the problem statement is simple. You are given an array nums, okay, an integer k, and also you are given queries. For each query you need to find an answer. So what is your answer corresponding to each query? In each query you are given a range, right, from L to R. So you need to find whether the corresponding subarray to this range is valid or not. What is the condition for a subarray to be valid? The condition for a subarray to be valid is it should contain exactly k distinct numbers, okay, and the frequency of every number in the subarray should be even. This is the condition. So if both conditions hold, then your subarray is considered valid. And for if your subarray is valid, then your answer is true, otherwise your answer is false. And at the end you just need to return your answer array, which represents answer to each query. Okay, so let's try to understand with the help of first sample test case. If we take an example of this first sample test case, we see that we are given this nums array and k equals to 2, which represents k represents your maximum number of distinct integers you can have in your current subarray. So first, if we see the first query 0 to 1, 0 to 1. So our numbers corresponding to this range is 1 to 2, right? In our original array we have 1 to 2, these are the numbers. So see that the number of distinct integers in this subarray are 2, right? Number of distinct integers, and this is less than or equals to k. So this first condition is valid. Now let's check the second condition. What is the second condition? The frequency of every number in the given subarray is even. Let's check that. So check that the frequency of 1 is 1 and frequency of 2 is 2. It means that frequency of both of integers are odd, right? So our second condition is not true here, right? In second condition we need to have the frequency of every integer in the subarray even, but here we have odd frequency of both of these integers. So second condition failed. So in this case we will say that the answer for this first query is false. Okay, answer for first query is false. Now let's check for 0 to 3. 0 to 3. 0 to 3 we have 1, 2, 2. You will say that answer for this is also false. 0 to 3. So 0 to 3 will actually contain 1, 2, 2, 1. 1, 2, 2, 1. So now if you see, what are the number of distinct integers? 2. 1 and 2, they are only two distinct integers. So you will say that first condition is satisfied because 2 is less than equals to k. Now also find the frequency of each integer. So you will say that frequency of 1 is 2 because it is occurring 2 times, and frequency of 2 is also 2 because it is occurring 2 times. So you will say that our second condition is also satisfied here because the frequency of each integer is even. So in this case your answer will be true. Okay, similarly you can check 1 to 2. 1 to 2, answer for this will be true because 1 to 2, if you see here 1 to 2, this is 2 comma 2. See that 2 comma 2, there is only one distinct integer, so first condition is satisfied because 1 is less than equals to k, and also second condition is also satisfied because frequency of 2 is even. So in this case your answer for this sample, your answer will be false, true, true, false, true, false. For third one you have false. How is it so? 1 to 2. Oh, note that your first condition was actually it should contain exactly k distinct numbers, exactly k. So you should have exactly k distinct integers. I missed it. So in this case you check that for this particular case, here you check that for first query 0 to 1, your answer will be false, right? Because this is satisfied, this condition is satisfied, 2 equals to k, right? Exactly equals to k, but frequency of each integer is odd, so your answer will be false here. Now if we check the second query, for second query distinct total number of distinct integers are k, right? First condition is satisfied, but second condition is also satisfied because the frequency of each integer is even. If we see the third query, for third query check that the number of distinct integers, that is 1, they are not equals to k, then first condition is failed here, right? So your answer for third query will be false. Okay, so this is how we can solve the first sample. Similarly you can see you can solve the second sample. It's not very hard. We just need to find these two conditions and check whether this subarray is valid or not. Now how you will solve this problem for a generally given array nums, for a general given array nums, right? And your value of k and your queries li to ri. You are given q queries, so you will see that your brute force solution will not work here, right? Iterating over each query, right? In each query you are given this subarray from li to ri, and if you in brute force what you will do is you will take an ordered map, right? An ordered map, and you will iterate over each of the integers in this range from li to ri, and at the end each time you will insert the integer in your unordered map and increase its frequency, right? So your unordered map will store unordered map int comma int. It will store the frequency. Okay, frequency of I frequency of I, f of I represents frequency of integer I in this subarray li to ri, right? So you will just iterate over li to ri and store the frequency of each integer in this frequency map, and at the end you will check whether size of f, if size of f equals to k and the frequency of each integer is even, then your answer for this query will be true, otherwise your answer will be false. So what is the time complexity you are taking here? Time complexity is order of q. Q is for iterating over each of the query, and n, q into n, right? Because for processing each query you are iterating over the whole array, right? Not whole, but in the worst case you will be iterating over whole array from li to ri, right? So for each query you are taking order of n time, and for all query you will be taking q into n. So this is your time complexity. But see that n and q both are order of 10 to the power 5. So this solution will not work here, definitely not work here. So if we improve this solution, what we can use is we can use square root decomposition. So if you understand the square root decomposition algorithm, what you do there is you just break your current array into some segments of square root of n size, right? You break your starting from 0 to length minus 1, then length to len minus 1, right, up to n minus 1. So you just broke your parent array, that is nums array, into segments of length len. What is the length len? This is square root of n. Okay, now square root of n, you just broke your parent array into square root of n. Now what you will do is for each of these segments, right, for each of these segments what you will do is you will calculate the same thing. You will store an unordered map. You will store an unordered map of frequency int comma int, right, where f of I represents the frequency of integer I in this segment, right? So for each segment you will store the frequency of the integers present in this segment using unordered map. Okay, once you are done with this pre-computation, now what you will do, you will iterate over each of the queries, right? So for example, right now let's say you have this query li to ri. Now what you will do is you will break this range into segments of length square root n, right? Segments of this length, that is square root n. Once you broke this range into square roots of n length subsegments, now what you will do is you will just iterate over subsegments, right? And for each subsegment what you will do is for each subsegment you already have an unordered map which represents the count, which represents the frequency of each integer, right? So which does have the frequency of each integer, But does it improve our solution? It doesn't improve our solution actually. No, actually I am mistaken here. This is not a square root. This doesn't help us here. The reason is, okay, so even if we iterate over the subsegments, right? Even if we iterate over the subsegments, let's say we just broke into some subsegments. Okay, segment 1, first segment will be actually starting from Li to some L1 dash, or let's say I1 dash, I1 let's say. Second segment will be I1 plus 1 up to I2. Third will be I2 plus 1 up to some I3. At the end, what do you have here? Your end will be, end segment will be ending at Ri. So these are the segments you broke this current subarray into the length of square root n. Okay, len, that is equals to square root n. Now what you will do is you will iterate over each of the segments, and you will also keep a track of unordered map, of int comma int, let's also call it frequency. So in this map what we are trying to do is we are trying to calculate the frequency of each element in this given subarray. Okay, so we will iterate over each subsegment here, and for each of the subsegment we already have an unordered map, right, which is storing the frequency of each element inside this subsegment. Now what we will do is we will just merge this subsegment into our current frequency map. How we will do? We will just iterate over the elements of this unordered map which is storing the frequency, and just add those frequency into our current frequency map. At the end, so we are iterating over square root of n subsegments in the worst case, right? So once we are done with this, we can easily check the condition. How? If size of frequency is equals to k and the frequency of each element in this map is even, then our answer is true, otherwise our answer is false. Now in the worst case, if you see the worst case, it can go up to order of n square. The worst case, this solution can go up to order of q into n, right? But in average cases, I think this solution is a little better over the previous solution in which we were just iterating over the subarray L to R. But in the worst case, we know that this can go up to order of q into n. So this is just the little improvement I was able to make, but I don't know the exact solution which authors are expecting from us. Okay, so these were my explanations to all of the 4 problems. If you have any doubt in these explanations, please reach out to me in the comments. I will reply. So this was it for this video. Have a nice day. Thank you.